Okay, folks, look, we're in section 4.5 right now, 4.5. So, what I want you to do is set up some notes like you see right here on the screen. Put the video on pause, whatever you need to do. I do expect you listening to the video, not just watching and reading closed captions, because when you're reading closed captions down here, it's really hard to watch what I'm doing up here on my work. So, thanks for considering doing that. All right, so look, what have we been doing? We've had equations like this, and we say, hey, I know where there's a zero. There's a zero at -2, and there's a zero at +3, right? We say there's an x-intercept at -2, and there's an x-intercept at 3. That's really useful information. If I can see it in factored form, easy to find the zeros. But what if I can't see it in factored form? They don't give it to us in factor form. Let's say they make it like you can't see the factors up here. Would they still have zeros? Like with this polynomial over here, if it is expanded correctly, if this guy was expanded correctly and it looks like that, let me cover that polynomial up. Would this polynomial have these zeros? It'd be way more challenging to find -2 and 3 if you didn't see it in factored form. So here's factored form, here's distributed or expanded form, right? Standard form. This is standard form when the degrees go down, like 3, 2, 1, and then 0, right? The exponents go down. You notice what I did here is I took this polynomial and I put it in a denominator of a rational function. So, like if we didn't see the factors in the denominator, it'd be way more difficult to find the vertical asymptotes. So we have some really good reasons, right, for finding these x-intercepts or finding the vertical asymptotes, and we don't have to use any kind of factoring techniques to do that. We can use some other ideas when it is like maybe beyond our factoring skills. Okay, so let me just see if I'm making this clear. If you had a polynomial like this, we would love to have it looking more like this over here in factor form so we can easily see the zeros, right? But what we're going to do is we're going to talk about some ideas down here that will hopefully give us some techniques to find those zeros easily. All right, the first one's called the remainder theorem. Now I'm going to write this idea down, and I want you to take some notes on it. It's okay if you don't understand it immediately, all right? So I'm going to use the same f of x up here. I'm not just writing a random f of x, so maybe I should change this guy to a different letter, like g of x. This guy down here in the denominator is f of x, and then we had some other function up in the numerator. That's what makes this a rational function, right? Let's call it like h of x, all right? Okay, so my f of x is this function right there. All right, let's say I took that function, f of x, and I divided it by x minus 3. Well, x minus 3 we know is a factor because what I did, I thought I'd make this clear, is I expanded all this stuff and wrote it in standard form, right? So we can see, look, x minus 3 is a factor, right? So whenever you're doing a division, like think of a really simple one, like let's say you're taking 15 and you're dividing it into, I don't know, 2,563, okay? What you're going to do is you're going to say, well, how many times does 15 go into 25, right? And it goes into there one time, and you put 15 down here, right? You subtract that, you end up with 10, you bring the 6 down. You say, how many times does 15 go into 106? Let's see, that would be, I think, oh man, what is that? 7 times, I think, 70, 30, yeah, 7 times. And so now we've got 105, and then I subtract that and I get 1, and then I bring the 3 down, right? And I say, how many times does 15 go into 13? How many times does 15 go into 13? It doesn't go into there evenly, so you put a 0 up there. And then you do this. You go like plus, this is one way of writing it, plus 13 over 15, okay? So keep that in mind. So this part, the 170 part, is called the quotient. It's like the answer, okay? And I'm going to put a little Q here for quotient. This 13 over here is called the remainder, right? It's called the remainder. I'm going to call that R. So over here, like when we divide by x minus 3, we're going to have some quotient, okay? And it's going to be q of x because it's going to have an x in it. And then we're going to have some kind of remainder. So the remainder is like the number that's left over, right? And you put it over what you're dividing by. So I'm dividing by x minus 3, okay? I know this looks pretty complicated, but I could simplify it. I could multiply everything in here by x minus 3. So if I do that, if I multiply everything by x minus 3, watch what happens. X minus 3 down here, these x minus 3's divide out. Over here I've got q of x times x minus 3. And over here I've got r of x over x minus 3 times x minus 3. And these x minus 3's divide out. Well, what the heck? I'm left with f of x is equal to q of x times x minus 3 plus r of x. Okay, now, why is this helpful? Well, if I do f of 3, think what would happen. If I put a 3 right here, I get q of x times 0, because I'm plugging 3 right there, right? And then I get plus r of 3. So what this really means is, if I evaluate f of x at 3, if I go f of 3 right here, I'm going to put 3 in here. Okay, I get 3 cubed plus 3 squared minus 8 times 3 minus 12. Let's see, I get 27 plus 9 minus 24 minus 12. Hey, that comes out to be 0. Wait a minute, that comes out to be 0. Well, I kind of knew that was going to happen. Like, if you look at it in factored form, isn't it true if we plug a 3 right there, aren't we going to get a 0, right? I mean, that's the whole idea. So 0 times who cares what else, we get a 0 overall. So if the remainder comes out to be 0, that means that 3 is an x-intercept, or it means that x minus 3 is a factor. Okay, that's really huge. X minus 3 is a factor. That's what this 0 right over there tells us. It tells us that 3 is an x. Let me make that clear. Okay, that looks like a one word right there. Is an x-intercept. Okay, so let's see. If I'm doing this work, that's kind of a bit of a hassle, you know, to plug 3 in, particularly if the function's way more difficult than this. I mean, this was a cubic. What if you had like a 5th degree polynomial or something like that? So I'm going to give you some techniques for making life a little bit easier. One of the techniques is called synthetic division, okay? So in video 2, I'm going to talk about this nested factoring and synthetic division. We're going to continue our notes from here. Thanks for following along, everybody. Appreciate it.